For students in the back, can you hear me? Okay, great. Thank you. So remind me if anytime the microphone doesn't work. Um, for the exam 2, I think the average is very reasonable. So I received some email saying that it's kind of unfair that I gave 10 points for bonus and raise average. I don't really know what it means. I mean, what do you guys do want me to do? They complain about that. So what? I'm a little confused by email. So the email communication kind of like I don't really so for anyone who really have some concerns about like 10 points raise average, please talk to me, so we can have a conversation. So I really need to know what you mean by it's unfair. I mean, if you guys all agree, I can remove that 10 points for everyone. I'm a little confused when I receive those kind of emails like, oh, I think this is unfair because the 10 points raise average. Yeah. I don't know what it really means. I mean, I can put the first problem 35 points back to 25 points and ask TA to regrade everything. So if you have any concern about like the extra points raise average, which you think is unfair, please talk to me during office hours so we can find like I need to know what you're really concerned about. Do you want we can talk. So please talk to me during about office hours. So based on email, I don't really know what you want me to do. And also, as I said, since like in the final grade, I make sure that 40% student will get A in the class and shift the grading. If it's lower than 40%, I will shift the whole grading scale. So in the end, the final grade, it really doesn't depend on like the level of difficulty of the exam or anything. So the final grade will be very reasonable. So you don't need to worry about too much about like one exam grade, those kind of things. You just need to work hard. So your job is to work hard in this class, and my job is to make your final grades reasonable. How about that?
Can you still expect project grades today?
That's my conversation with the TA on Wednesday, and he said yes. Okay. Let's continue with class last time. Since we didn't have a class on Wednesday, let's do a quick review of what we did on Monday. So we started the full node rectangle element, which is one type of element we use to model plane stress. Plane stress, we talked about the CFD. Now this is the full node rectangle element, and I emphasize that for this one, if you want to use the equation we use, it has to be all edge parallel coordinates. And I got a question after class like, what if it's a full edge, some random shape and not parallel? We have a separate chapter to talk about. Chapter 7 is called isoparametric mapping. But for this chapter, everything derived here is only for all full edge parallel to the coordinates, and only for this first node, second node, third node, fourth node. You cannot rotate node order. So it was a minor mistake in the textbook. So when you read textbook, you will see there are conflict of things there. Well, I already tested for you guys, and I already talked to Dr. Kim, who is the first author of the textbook. We all agree that that was a minor mistake. So this should be the first order node, second node, third node, and fourth node, because our derivation is based on those node order. And we talked about the interpolation, since for displacement, let's say for U and V, they are independent. So for the U, since we have 4 information, U1, U2, U3, U4, we can have 4 unknown coefficient, alpha 1, 2, 3, 4. And for this polynomial, of course, from the constant term to x term, y term, and xy term. And for the derivation part, we use the understanding of the shape function to simplify the derivation process. So as you can see here, shape function N1 means that it needs to be 1 at node 1 and 0 at all other nodes, which means that it should be 1 here and 0 at node 3, node 2, and node 4. So it basically means that on this edge and this edge should all be 0. And since we have the expression of these two edges, so basically what we did is that we multiply this component and this component. And if it's any point on these two edges, it can make this multiplication equal to 0. Right? Any point, you find any point and put coordinates into this expression, it will make it equal to 0. And to make it equal to 1 and node 1, this is simple. In the denominator, I just simply put a minus x1 minus y1. So when you plug in x1, y1, and then this coefficient equal to 1. So similarly for the n2, n3, n4, and now we got a shape function because the denominator, this is area, area, negative area, negative area. So this is a simplified method for finding the shape function. And of course, in the textbook, you have a Lagrange interpolation for finding shape function. You can read the textbook for that part. And also for displacement in the y direction, v, same thing, n1, v1, n2, v2, n3, v3, n4, v4. Shape function, they're exactly the same because derivation part, there's no difference, right? And similar to CST, when we talk about there's a point on the edge, we don't need to go through like finding all the shape function and doing interpolation, that kind of thing, because you can just imagine I show you this graph in the last class. Let's say this is the shape function of n1. And if somehow we also plot shape function n2 on this graph, then it should be something like this. And also, yeah. So let's say if we only take the 2D situation when y equal to 0 and on this plane and plot shape function it simply becomes something like this. And so this becomes n1 and this becomes n2, and it get back to what we learned in the CST. I talk about the 1D interpolation here, exactly the same, right? So this is n1, this is n2. n1 equal to 1 minus s and n2 equal to s. And you just need to know the displacement at two nodes. So this is this can save you a lot of time instead of going through the whole process of finding shape function n1, n2, n3, n4. Because if it's a point on the edge 1, 2, it does not really depend on n3 and n4. n3 and n4 on edge 1, 2 is 0 anyway. So this is same as CST element. And we also talk about, okay, now we have the interpolation part, which is if we know the nodal degree of freedom, how to find the nodal degree of freedom at any point within the, including on the boundary of the quadrilateral element. The other thing is that next step is calculate strain. So strain based on definition, this is the definition from mechanics materials. And of course, similar as what we did in the CST element, the derivation, the partial derivation of the u with respect to x is basically shape function with respect to x and shape function y, and this is shape function x and y. U and v here, they're constant. So this is a shape function. So if we put the calculation in the matrix equation form, then it becomes, as you can see, I can show you one example. Let's say partial derivative of n1 x, this is n1 x, and you can see here 1 over a common coefficient here, and there's negative x, so it should be y minus y3, y minus y3, right? And the same thing, you can check all the others. So this is n2, partial derivative n2 with respect to x, n3, n4, and this is for y. And when we put it into matrix form, this is a B matrix for the 4-node quadrilateral element. And the last class, some student asked me like, oh, okay, there's x, y here, what does it mean? So this x, y, they are variable here. Of course, when you see like sub 1, 2, 3, 4, they are the coordinates of the 4 nodes. So they're the constant. Whenever you see x, y, it means that, well, within this quadrilateral element, when you plug in different y, which means at different point, you actually have different B matrix. Does it make sense or not? And basically, it means that, okay, normal strain in the x direction is actually linear change in y, right? Normal strain in the y direction is linear change in x because we do have the x variable here. And shear strain is linear in x and y because it had both x variable and y variable. So when I plug in different point, so let's say if my point is moving from here to here to here to here, the B matrix the change. So this also explains that why the CST element is the most fundamental and the simplest element. Because CST, there's no variable in the B matrix. If you guys don't remember, I can show you the B matrix for the CST here. Okay, so this is we test in exam 2. So this is the B matrix for CST element, and then you can see that the B and C they just calculate based on the X and Y, right? So it's purely dependent coordinates. There's no X variable, there's no Y variable. That's why it is called constant strain, because it does not depend on X, does not depend on Y. When you have a CST element and when you move the point to different location in the CST element, you get the same B matrix, right? It's called constant strain or constant stress. That's why now I'm showing you here that because B matrix here does contain the X variable, Y variable, so it's a more advanced element. So basically it means that it can show certain of linear change for strain in the X, strain in the Y. Right. So this is a theory part. Let's do a example problem here. Similar situation, we have one element in the XY coordinate. So of course, node 1, node 2, node 3, node 4, and coordinate for each node. This is a 0, 0, of course, and x equal to 3, y equal to 0. x3, y2. Node 4, x0, y2. Coordinates of 4 nodes. And for the node degree of freedom, u1, v1, u2, v2, u3, v3, u4, v4. So the u1, v1, 0, 0, u2, 0.1, v2, 0, u3, 0.2, v3.1, and u4 is 0. And v4, I don't know what I'm doing here. Sorry, 0.2. So we need to figure out, find displacement in X and Y, U and V, and also strain. Normal strain in the X direction. But of course, you should be able to find all the other 2 strains also if you know how to find the strain in the X direction. I just want to save some time here in the class. Just use 1 strain components. At 0.21. But of course, this one, I do expect to practice the standard procedure. So the point itself is within the element. The point itself is within the element, it's not simply on the edge. So because I do want you to practice like how to use our standard procedure to find the displacement for random point within the element and for the strain, 1 strain component. And I expect you to be able to solve the displacement and also all the strain components in your own practice. So for this one, of course, since our shape function are here directly, we just use this one, right? Based on the coordinates of 4 nodes, we find the 4 shape function. So to save some time, let me just copy and paste. So based on the coordinates of 4 nodes, we can write the shape function for our element as the first one. So the area is 6, right? 1/6 and x3, y3, plug in. 3 minus x, 2 minus y. Shape function n2. 1/6, x1 equal to 0. So there's negative sign here, there's negative sign here. So cancel. Y3 minus y. 2 and 3. x1, y1, 0, 0. Negative sign, negative sign. So it becomes x, y/6. Shape function n4. y1 equal to 0. Negative sign, negative sign. So it becomes 1/6. x3 equal to 3. Y. So this is the 4 shape function for our 4 node quadrilateral element.
Is there something else
You are correct. Actually, for everything related to 0 displacement, yes. If let's say u and v both are 0, yes, you can skip, of course. But I'm just showing the standard procedure. Yeah. Yes. So in your exam, like or in your homework, if you know that some information that not necessary, you can complete. I actually encourage you guys to skip it, so to save you some time. And it's true that since u and v for both of them, they are 0 at node 1, so we don't really need this shape function. Correct. Any other question? Okay, now let's do the interpolation. Again, I write the complete equation just to be complete here. U x y n1 u1 n2 u2 n3 u3 n4 u4. And now we see that u1 u2 u3 u4, we have 2 0 components. So basically this one is 0, this one is 0. We only have 2 terms. So let's plug in numbers. So n2, this is shape function. And u2, displacement u2 equal to 0.1. And n3, and u3 equal to 0.2. So this one is displacement at 0.21. We plug in x equal to 2, y equal to 1. Makes 2, y equal to 1, u3 equal to 0.2. So this is 0.1. This is displacement x direction at that point. And similarly, for displacement in y, v, x, y, we have n1, v1, n2, v2, N3, V3, N4, V4. Now let's check the nodal degree of freedom. We have V1, V2, V3, V4. Again, we have 2, 0. So the first two terms, they're 0. So this one is 0, this one is 0. We only have N3, V3, N4, V4. V3 equal to 0.1. V4 equal to 0.2. And plug in x equal to 2, y equal to 1 for displacement in the y direction. We have 2, 1, 0.1. 1, 1, 0.2. So this is for displacement interpolation, x, y, the same procedure. For the strain calculation, again, since we already have the B matrix here, actually, it's only asked for one component. Okay, then we don't need matrix. We only need this component. But of course, it's the same way to calculate this one and this one, the same thing. So if we only need this one, it basically means that it's equal to 1 of A and this row times this one, right? And of course, we only have 2 terms because U is only related to all the U's, and U we have U1 and U4, they are 0. So we only have 2 terms. It's Y3 minus Y times U2, Y minus Y1 times U3. Make sense or not? Right? All the components that multiply with V, they are 0. And for all the components multiplied by U, we have 2 U1 and U4, 2 components that are 0, U1 and U4 that are 0. So we only have 2 components left. So this one times this one plus this one times this one. It becomes the normal strain in the x direction. But of course, don't forget the 1 of A. Plus Y minus Y1 U3. So 1 over 6 2 U1 equal to 0.1 and Y1 equal to 0, Y U3 equal to 0.2. And of course, we plug in, it's not related, there's no X there. So plug in Y equal to 1. I forgot, I think this is 0.1. Sorry about that. This. So 0.1 plus Y equal to 1, 0.2. This is normal strain in the x direction, but of course you can calculate normal strain in the y direction shear strain in a similar procedure. Any questions so far? Okay, so you should expect that the next step should be finding the K matrix, right? Because it's the same procedure in the CST. We first did the interpolation and derive the shape function and talk about the K matrix and how to put the F force applied into the F calculated that F vector, and then solve unknown degree freedom and calculate use the interpolation here, calculate strain and calculate stress. So here is the same procedure. We are done with interpolation and the strain definition derivation. Let's find the K stiffening matrix for 4-node rectangular element. I think this is in chapter 6, section 4.2. Stiffening matrix for 4-node rectangular element. And derivation part is also very similar. Remember in the CST element, we had the strain energy equal to integration of the strain energy density integrating the volume of the CST element. Here the same, we integrate the strain energy density into this 4-node rectangular element. Integration over the volume. So the strain energy density is always half of strain times stress. So the derivation part is very similar, just the B matrix is different here. So let's say integration of the strain energy density, which is half of strain times stress, dV. And again, we assume the area of rectangular element equal to A and assume the thickness of the rectangular element is H. This volume we can write as half of H. Since there's nothing really changed, we are talking about the plane stress, so there's really nothing changed in the Z direction. So the integration we can simply write as half of H and dA, integration of the area. And we also talk about that the stress equal to B matrix times strain, and strain equal to, stress equal to C matrix times strain, and strain equal to B matrix times Q, no degree of freedom. This is the same here, just the B matrix is different. So let's write here. It becomes Q transpose B transpose C B Q vector dA. Let's still use different color to help you guys understand. So this part is equal to blue. And no, this color is not. Yeah. See this one. And for the strain, so strain equal to B times Q. Strain transpose, we need to switch the position, so it becomes Q transpose times B transpose. Make sense or not? And for stress, it's strain times the C matrix. So C times strain equal to B times Q. This is the same as what we derive in the CST element. But now here's the difference. Because in the CST element, this one is a constant. This one is a constant, right? So we can simply remove the integration and simply write as, okay, water volume, so it's H times A becomes the volume of the element. But here, since now for the B matrix here, it does include X variable and does include Y variable. So we do need to do the integration of each component. it's not as simple as we remove the integration and become the volume. It's constant. No. Here, B and B transpose and B here, they do contain the X variable and the Y variable, and integration area, we do need to calculation for each component. Don't get scared. I will not ask that in the exam. So now let's write this one as, again, similar as what we did before, we always want to separate Q transpose and Q to two sides, and whatever left in between should be the stiffening matrix 1/2, and move the Q vector here. And the thing in between becomes H integration B transpose C and B. Integration over the area. dA. And now this part becomes the stiffness matrix for our 4-node quadrilateral element. Let's use a different color. So this is the K. What dimension of K? What dimension of K? Yes, thank you, 8 by 8. So you can see here, 3, 8, right? So basically you have, let's move this one here. So this one is 3 by 8. C matrix is the same, no matter it's CST or 4-node or you will see in the tutorial I talked about LST and for 8-node quadrilateral element Q8. C is always the relation between strain and stress for plane stress situation. So C matrix is the same. It's always 3 by 3. And also B transpose now becomes 8 by 3. So the B transpose times C times B is 8 by 8. Or you can simply consider the dimension of K matrix really depend on our nodal degree freedom for this element. And for our 4-node quadrilateral element, we have 4 nodes. Each node has 2 degree freedom. So the total degree freedom should be 8. So the K matrix should be 8 by 8. Make sense or not? The next step is calculation. So you can calculate this one transpose times the C matrix, similar as CST element, same as CST element what we talked about in that section, times B matrix. And you have 8 by 8 matrix, and each component in this 8 by 8 matrix, you have X variable and Y variable, and you need to integrate over the area for each component. Of course, I do not expect you guys to do hand calculation for this part. So of course, this one can be done by Abacus, but I do want you guys to know what is Abacus actually calculating when you put everything like discretize using the Q4 or Q8. So this is just help you understanding the procedure, basic procedure for finite element analysis for plane stress situation. Here I can give you a matrix for a square element, which is a special case of quadrilateral, 4-node quadrilateral element, because I talked about it. I think there was one student asked like why the shape function is plot on the edge length, they are not equal, because whatever we derived here is really for the edge length can be anything, right? As long as it's parallel to the XY coordinates. And for each single Q4 element, you do need to do the calculation by yourself using MATLAB or just put into the Abacus for the calculation directly. I do not expect you guys to do the hand calculation, but I do give you a 8 by 8 matrix for a square element. Hopefully by now you guys can understand why I keep emphasizing do not try to be perfect to write every component in the matrix, because there's no way you can solve the real life finite element problem if you really stick to like I need to be perfect in every matrix, no matter what dimension of the matrix. I can post this one on Canvas later, or you can take a picture now. So this is a stiff matrix for square element. For any other like rectangular shape, not square, you need to do the calculation by yourself. So this is only for square. Yes. This is the K matrix. And you may wondering like, okay, even for square matrix, we have square matrix like small square and bigger square, right? The edge length of square can be different. Why here, as you can see, this 8x8 matrix, it does not really, there's no edge length L. So basically mean that no matter it's small square, larger square, the K matrix is same. Anybody know why? Why? I mean, for square, it can be like the edge length can be 1, can be 100, can be 1000. But why the K matrix is same? It fit all sides of the square element.
That they cancel out when you do when you do the multiplication with when you have the E transpose and wouldn't the areas would cancel out and the side lengths are all the side lengths are all the same.
It's L cancel out. Yes, you're correct. Yeah. So yes. So it is in the calculation process, because we know that K is really making the relation between the force and the nodal degree of freedom, right? And it's a relation between the force applied and the displacement. Makes sense or not? So in the calculation process, the L somehow cancels out. But of course, I'm not going to do demonstration for the B transpose times C times before the 8x8 matrix to show you how to prove that it's cancelled out. But I will use a very simple example, the 1D tension compression situation, to show you why it cancels out the dimension. So let's say if we have a very simple situation and we use a square element to model it, I use 1D tension compression situation. And of course, I use roller support here and pin joint here. And I assume that I apply force, only tensile force. Applied on this square element. Edge length, I use L here. So what we learned from mechanics materials, first chapter, first section, is normal stress equal to force applied over the area. And again, we assume the thickness of the square element is H. So now the stress here should be the force applied to F. Area is a cross-section area, should be H length L times H, right? So this is stress. And from stress to strain, we know that since it's 1D tension compression, it's the Young's modulus. So strain equal to stress over Young's modulus. And EHL. 2F over HL, this is the stress, over Young's modulus is the strain. And since we want to find the relation between the displacement and the force, we can write one step ahead. So now the displacement, I use U equal to strain times orbital length L. Makes sense or not? strain times L equal to displacement. And now you can see that 2F over EH. Now you can see that in the process, there's L here in the denominator, and then times L, it cancels out. So this is a simple way to explain to you guys like why for square element, it only depends on the thickness, Young's modulus, and Poisson ratio. Because now 2D, we need to consider the like lateral contraction, the Poisson ratio effect, but this 1D, it simplifies the situation. It does not really depend on the dimension of the square element. So hope you guys can understand better through this very simplified example. The K matrix doesn't depend on the dimension of a square element. But of course, in the homework in the exam, this matrix will be provided, and your job is to find out the components that you need to use in your calculation. Basically, of course, if I write the row index here, it should be simply as U1, V1, U2, V2, U3, V3, U4, V4. And same thing here, U1, V1, U2, V2, U3, V3, U4, V4. You just need to figure out, like, based on the boundary condition, what are the components can be deleted, what are the components that be used for calculating the free degree freedom. So now let's assume that we solve the K stiff matrix problem. For most situations, you need to use MATLAB, or you import your model to Abacus to do the calculation directly. We have 4 minutes left. Let's continue the next class. The next topic is how to put the equinodal force into the F vector, but we can talk in the next class. If there's any grading mistake in your exam, talk to me after class or during office hour.